So, welcome to the class. Today we're going to look into underfitting and overfitting under the important clarification series. So, during the development of machine learning models, people often come across this kind of confusion as when do we declare a model as having been underfitted or overfitted. And unfortunately, underfitting and overfitting, they go hand in hand. While you try to solve the problem on underfitting, you might end up overfitting. You will end up getting overfitting problem. So what do they mean and what is the meaning? How can we avoid them? How can we recognize that this is overfitting? Because we have also seen people that throw away their model thinking that it is overfitting. Meanwhile, it is not overfitting. So what are the yardstick with which you can use to be able to identify when your model is overfitted? And then what can you do? Is there any model or is there an algorithm that can always guarantee for you that you are going to get a model that is not overfitted? So we are going to look into a couple of this. So to understand the underfitting and overfitting, as we know, we have to first of all remind ourselves about the concept of inductive linear hypothesis, which is the brain behind the machine learning principle. The inductive linear hypothesis states that if the hypothesis works on enough data, then it will work on new examples. These new examples they are what we usually refer to as the testing set. We are saying that when we use the training set, if the hypothesis works for enough data, that is the hypothesis function that we have selected that the algorithm detected to be appropriate for this data, if it works on enough data on the training set this time around. However, we have a couple of terms. What is enough? Enough is a relative term. What is enough in a particular area might not be enough in another area. You see, with hardware by 100 sample might be enough. In another case, 22 might be enough. In another case, even 1,000, you are struggling to get it to be enough. So there are a lot of things that are involved. And that is why, again, we always remember, let the data speak. Let the data speak. So different data comes with its own unique information that is inherent in there. However, the hypothesis learning is very, very unique. So if the hypothesis work on enough data, then it will work on new samples. This is the standard thing. So that if I have my training sets and then I'm able to train it very well after training, and I show it back, you see, when during the training, this is why we go to also look at generalization idea. This is the training set. This is when we talk of if the hypothesis work on this one, if it work on this particular training samples, on enough training sample, then it should be able to work on new examples like this one, the testing set. However, underfitting and overfitting is a concept that is trying to let us realize there are situations whereby it doesn't work on this, it does not work on this. And in another situation, it will work on the training set, but it doesn't work on this one. So which one is underfitting, which one is overfitting? See, underfitting is where after doing the training, it doesn't work, it doesn't recognize the training set, it does not also recognize the testing set. However, overfitting is when it only works on training set, when you have new example that has not been seen before, it doesn't work. So what is responsible for this? And how do we deal with it? How do we even recognize that problem? Now, so during the training, as we know, we have these are the samples. These are the training. We have the label. So this are Apple. You give this one to the machine learning algorithm. This is Apple coming in. This is Apple coming in. For all these, you show it the output. This is Apple. This is pear. This is tomatoes. And then after the training, now we still give back each of these to check the training accuracy. We've explained this concept in our previous videos. We need the training performance. So after we introduce each of the training set, and then we tell that, okay, this is the output, this is Apple, that is training under the teacher. Then we need to then put back the training set without telling it the output. What we have trained you on, at least you have seen them. Okay, now we're going to give them back to the model after it has finished training. But this time around, we don't give the output again. We want to check if it's able to recognize what it has seen before. Now, if it's able to recognize it, then we don't celebrate yet. This is the one that we mentioned here under the if the hypothesis works for enough data. So after the training, then you give back the training set and see to want to check if your model is able to recognize what it has been exposed to. If it is positively recognized, negatively recognized, it's able to differentiate the positive and the negative. If it is a multi-class problem, it's able to achieve reasonable outcome. Then we say, oh, the training set has worked, provided it means the data set is enough. Now we need to move. The assumption in inductive learning hypothesis is if it works for those training sets, then it should be able to work on new examples. Otherwise, something is wrong. Because this particular testing set is part of this training set originally, but we divided them into two. We separated the testing set apart, and when you use the training set on the model for building. So since the data set is coming from the same area, the same distribution, it is assumed that if everything is okay, all things being equal, then if it works on the training set, it should be able to recognize the unseen set. This is the big and basic principle behind machine learning. Now, so once we give back the testing set, we want to see, is it going to work? That's why we answer the question, how well does a learned model generalize from the data it was trained onto a new test set? So after we have checked the training set performance, we now say, okay, now let's go to testing set performance. Sometimes we have training set performance at, let's say, like 25% accuracy. So then the testing set performance, let's say we have like of course, if your testing set performance is 25%, you can be sure that the testing set is going to be maybe worst, maybe 16% accuracy. For sure, something is very wrong. In this case, we say this is underfitting. This is called underfitting. It means your model is not able to understand what is inherent in that data. It's not able to model the data effectively. And then we go back and say that if the hypothesis works for enough data, it means the hypothesis doesn't work for this data because of what you are getting. You see, it's not working for it. However, there are situations again whereby you are getting like 98% accuracy here, but when you bring in the testing set, again, you are getting like 35% accuracy. This is huge performance on your training set. This is very, very poor performance for the testing set. They will say something is wrong again. It's able to perform on the training set. If at some time you might get 100%. It's able to recognize all the training set, all of them. However, when you give it the testing set, sometimes it's even performing 25 or even 10%. It's not able to generalize. It means it failed this hypothesis function theory principle. It works on enough data, then it should be able to work on new example, but in this case, it doesn't work. That is what we call overfitting. You see, this is called overfitting. Once overfitting takes place, your performance will be good on the training set, but it's not going to be good on the testing set. But the underfitting, you have the two sides are bad. Not good for training and also not good on the testing set. So underfitting is still it's easier to recognize because you are not going to stop. You know that, no, my model is not able to do this thing. However, overfitting is a bigger problem because some people mistakenly, when they get very high accuracy, like 100% in the training set, they start celebrating, oh, we got excellent result. Not waiting to check the testing set. That's why you don't talk of getting better result when you have not checked your testing set or validation set, as the case may be. Now, as we discussed before, you all know that when we want to, how to check the generalization ability of model, we've described this one. Either you use the holdout method, whereby we divide the data into two sets, training set and testing set, or three, training, validation, and testing set. In any of these, the system is only allowed to see the training set and the output of the training set. And then later you can check the performance on the training set. What I've training you on, are you able to recognize them? That is the essence of getting the training performance. It's very important. However, you don't use training performance to judge the performance of your model. We need to clarify this. If you are getting 100% in your training set, performances, this doesn't make it. It doesn't make, at least the good news is that, okay, it's working on enough data. But the second part of the hypothesis story is yet to be established. Until you have now used your validation set or testing set and you are still getting something closer or something reasonable, you're getting like 75, even sometimes 65%, it's okay. You see, maybe you still need to do your hyperparameter optimization and the likes. However, the moment you start getting 100% in training set, then you should be aware you might be running towards overfitting. Because sometimes it's better for us to get like, it's better for you to get like 92% accuracy, compromise in the training, so that you can get like 80% or 89% in testing. This is better. You see, because sometimes people, oh, I want my training set to performance to be very high. The more your training set is getting really high, you might actually be forcing your model to memorize, as we are going to show us shortly. So we have other methods like the end-fulcrum validation, which we presented in last couple of weeks lecture. We can refer to the video. These are different ways by which you can check the generalization abilities of your model, because this is what is important, by the way, actually. So, and as we described this earlier, so machine learning building model is an iterative pattern. So in which case you always have that freedom to go back, keep changing your modeling, checking the upper parameters, changing the algorithm altogether. Maybe the algorithm is not working because there's no free lunch theorem is saying there's no algorithm that works in all situations. If one algorithm is not working, check another algorithm, check a couple of algorithms, and then see, maybe you can get your work better. Now, to understand underfitting and overfitting concept very well, we have to bring in a concept that we know as bias variance trade-off. There has to be a trade-off between the two, bias variance trade-off. That is, the two of them are the opposite direction. As you try to reduce bias, variance is increasing. As you try to increase variance, bias is going to be increasing. So that's why you have to balance and stop at the appropriate place. Now, we say, how do we know if a model is performing well? We say a machine learning model is performance is considered good based on its prediction and how well it generalizes on an independent test set. So once you have trained, and then you check it on the test set. So based on the performance of different models, we can choose the model which ranks highest in performance. That's why in machine learning, we always encourage that we run as many algorithms as possible. Don't just pick one algorithm and say, oh, this algorithm is well trusted. It also will get better results everywhere. No, it doesn't guarantee that it's going to get good results for your own data. That's why you expose yourself to a lot of algorithms, try them out, and then you can select the one that is able to model the data in the best way that is possible. Now, let's look at this example of predicting election results. You gather the data from one region, and then you train the system on the basis of this single regional data. That is, if it works fine, that is the first part of the inductive learning hypothesis. Now, can we apply this prediction to entire country, county, or the state, and to the national level? This is what you want to check. You want to generalize that model you have trained on a particular data. You want to generalize it to data set. Of course, they all belong to the same type of data, but however, maybe coming from another zone or another region. So sometimes it results in prediction error. So what is the amount of prediction error that is acceptable? Which one is overfitting? Which one is underfitting, as the case may be? Now, again, how do we know if a model is performing well? Continues. We say, assume that an input X, and then we apply a function F on the input X to predict an output Y. This is the hypothesis function. We've explained this concept earlier on. Now, so when you have, there is an output given to you already, which is Y, then this is your prediction Y prime. So the difference between the actual outputs and the predicted output is the error. This is the error. So this is your predicted output. This is the original. What is the difference between the two? This is the error. Now, so the goal of machine learning algorithm is to generate a model that minimizes the error of the testing set, on the testing data set. That we want to minimize the error that is going to come from the testing set. Otherwise, if you are not able to generalize to the testing set, the effort spent on the training is almost near useless. Now these are the components of error. Error is actual prediction minus the predicted outputs. And then we have the component of error. Usually, error is defined as a reducible error and irreducible error. So the irreducible error, I'm going to explain this concept shortly. Why the reducible error, they are also defined as the bias and then plus the variance. Now, this is the entire error. It's made up of noise. Noise, this is coming from your data. This is coming from your data. Why? This is coming from your data. This is coming from your data set. Excuse me. Now, so the error is made up of the noise, then the bias, and then the variance. This noise is coming from the data set. And we often call it unavoidable error or irreducible error. There's nothing you can do about it, except you go back to your data and clean your data, check the outlier in your data, and so many other pre-processing you can do. And sometimes, no matter the pre-processing you do, it might not solve the problem if the data is really, really bad. So this error, you cannot use manipulation of hyperparameter to solve that problem because it is inherent in your data set. And as we always say that, let the data speak. This is very, very important. Now, so the error is made of these three. Then the bias and the variance, this is error due to incorrect assumptions during your algorithmic developments. And this is variance, which is error due to variance of training samples and other things that are allocated. So we're going to share this particular content. We can read more about some of these bias variance trade-offs. These two are the ones you can actually manipulate. We can try to check it. You can try to change the parameter of your algorithm, hyperparameter, in order for you not to go towards too much to the left or too much to the right. So you're on the middle course, as the case may be. Now, but for this one, it's unavoidable error that comes from your data set. If after checking everything, you are still not getting what you want, then you might need to go back to your data set. And that is why, like we told us earlier, machine learning development is an iterative process. You have that freedom to always go back to modify. You can go back to your data here. This is what I'm saying. Maybe your data has a lot of issues. This is why you are not able to get what you are looking for. You need to go and do more pre-processing. And we already explained before, we don't need to get stuck with pre-processing for too long. Let the data speak. Check it. It's when you cannot get what you are looking for, then you can go back again and then double check your data second time, third time, fourth time. And possibly you might have to ask your client to supply a new data set in a worst case scenario where the data provided is not actually providing the needed information to make the expected prediction. Now, having said that, we said the component of generalization error. So we have the bias, which is how much the average model over all training set differ from the true model. So we said this is error that is due to inaccurate assumptions or simplification made by the model. And I'll show a grammatical representation of this to make it easier. While the variance is how much model estimated from different training sets differ from each other. So depending on how you have partitioned your data, is it randomized, is it not randomized? So at some point, one data a sample might belong to the training set, in another time it might not belong to training set. How much effect does it have on your work? And now the main culprit we want to look at is underfitting and the overfitting. We said underfitting is model is too simple. When you say underfitting, model is too simple to represent all the relevant class characteristics. How simple is your model? See, if your data is complex, then the model could be too simple to be able to do that. Then how do you recognize that your model is too simple? A simple model is a model that is too simple. It's good to have simple model. Like we said, in machine learning, you always start from simple model to complicated one. But you can see here, we say too much of everything is bad. So we are not talking of simple model. There are difference between simple model and too simple model. So sometimes your model is too simple to be able to take care of the data set. Maybe data is complicated, it's complex. In this case, the attribute you are going to look out for. Too simple model is characterized, or underfitting is characterized by high bias and low variance. High bias and low variance. To understand in a layman term, it means you are going to get high training error and high testing error. So the model will be bad for both training set and testing set. So for example, you could be getting 25% training set performance and another 16% testing set or something closer. It could even be 35 or anything in the range that you yourself will know that no, this is unacceptable for both training and then testing. Now, then this is underfitting. As for the overfitting, here model is too complex. You can see it. Sometimes you have sophisticated model, as the case may be. Overfitting. We say here model is too complex and it fits irrelevant characteristics or noise in the data. You see, the idea is it's good for your model to have the capability to really understand the data set in deeper form and be able to express it. However, just as we always say in a real life situation, we say too much of everything is bad. You see, if it is too complex model means it's able to recognize some of the intrinsic hidden information inside the data set, which is what we are trying to extract in data mining or machine learning. However, because of that too complex nature, it fits irrelevant characteristics. It could be noise, it could be any other thing in the data set. How do you recognize your data, your model is already overfitted? It is characterized by low bias and high variance. You can see it's opposite of this. This is high, this is low. This is low, this is high. That's why the two are opposite. As you try to reduce bias, variance will increase. They are not on the same side. I will show you the grammatical representation shortly. To a layman, this is the simpler way you can recognize your model is overfitted or not. That is, you are going to check it. It's going to have low training error. You see, while having high testing error. Now, when you say high testing error, it means low performance accuracy. Because when you talk of error, if I want to calculate the accuracy or how good you are, that is the performance. What is the accuracy? That is the performance percentage of the improved accuracy minus the error. So if you have error is going to be 100 minus your error now this time around. So you're going to have higher error for the training set, while the performance is going to be very low, or as the case may be. So in the overfitting, there will be low training error and high testing error. Low training error means, in terms of accuracy, maybe you are going to get like 100% training, in which case error here is 0%. It's 0% error. Low training error. Or it could be 99% accuracy, in which case the error is going to be is going to be 1%. So you're going to have very low training error, but high testing error. The error will be very huge, in which case you could get like 20% accuracy, which means you are getting like 80% error, which is really huge. Meanwhile, you got 100% accuracy, 0 error. How do you move from 0 error to 80% error? That is overfitting. and what is responsible for that. So that's what we just summarized. So for underfitting, you have high training error and the high testing error, whereas this one is going to be low training error and high testing error. You can see it the opposite. The two of them are bad, but underfitting is easier to detect. Because once both your training set is not performing, you will not stop. You start trying. However, sometimes people make mistakes because they see the training error here is very excellent. They stop making attempt to make it better because it's already getting 100. Then by the time they're going to bring the testing set, they find out that they have not done anything. The system is not able to generalize to new sample. So it's a more complicated problem when you run into problem of overfitting. And this is how you can recognize it. You can represent it diagrammatically, in which case we say here, this is a sample. These are sample. These are the training sets. See? Now, a good model will be like this. See? However, this is our own too simple model. Too simple model. You know, this is underfitting. Here is an example of an underfitting. You can see here, the model has very few parameters. Too few parameters. Model with too few parameters are inaccurate because of a large bias. Not enough flexibility. Not enough flexibility. So you have a straight line. The parameter number is just too small. The parameter number is just too, the number of parameters is too few. Only one. So you can see that the model is not able to represent the attribute of the data. Look at some data set here, some are here. It's just a straight line. It's too simple. So when you bring in testing set, there's no way it will be, in fact, the training set is not even working, because look at it, this is a sample. Look at how far the sample are to this line. They are too far away, because we want a model that can represent. This is why this is the ideal model. You can see this line. This is a D model. It's able to represent then that each of the samples for training, they are not too far away from this model. But this one is too simple. It disregards the nature of the data set. So we said this is because of large bias, not enough flexibility. Now, in the other way around, sometimes when we have underfitting, people try to make it better to fit the model in a better way. They run into the second problem. Okay, since this model is too straightforward, just a straight line, then look at the second example. It's not okay, I'm not going to make it to be too simple, I'm not going to make it complex, then it becomes too complex again. See? That is, you want a model that will be able to pass through every data point. I want you to be close to every data point. You can see passing through almost the distribution pattern of the data. See, we say this kind of data, model with too many parameters, you can see too much parameter. Cover this point, at this point, at this point, too complicated, too complex. We say too much sensitivity to the sample. Take, for instance, is trying to go to be able to represent the location of every data pattern. If, let's say, this data actually could be an outlier, or the data here could be an outlier, could be a noisy data. It came down here because of this data, which may happen to be an outlier. That is why it is too much sensitive that it fits even irrelevant information in the data set. So this is the normal model that we are supposed to have, this model. You see, even though there's going to be a mistake, this kind of model maybe is going to get like 98% accuracy, but this one, the normal one, might get like 95% or 92%. This is fine. We don't need to get 100% or 99 or 98 before we get a good model. Because what is important is a model that is too complicated like this, it will memorize the inputs during the training set so that it gets very high accuracy for you. By the time you bring in the testing set, it's not going to be able to recognize what you just brought in to be checked as the testing set. So this is how we be able to recognize this is an overfitted or an underfitted model. So this one definitely represents a classical underfitted model because the model is just too simple. It's not considering the inherent attribute of the data set. While this one again go to the extreme, while try to avoid underfitting, then went to the extreme of overfitting everything. So the trade-off is the tension between the error introduced by the bias and the variance. So we have to make a trade-off. You see, there are some bias that will be allowed, some little variance. You cannot achieve full bias, because if you go to the bias fully, you are going to run to no one problem. If you run away from it too much, you're going to run to another problem. So that's why I'm going to show us a kind of practical demonstration of it. See, this is your bias variance trade-off. This is a kind of complexity measure. See, you can see here, this high bias, low variance, this side. This low bias, high variance, the other side. Now, this is the error. This is the training error. You can see as you keep training your model and the training error is reducing, the testing error is also trying to reduce along the way gradually. Of course, we always expect the training error to be less than the testing error. This is normal. The training error should be less than the testing error. This is normal. So in case you are having like a 98% in your training and 90% in testing, that's still okay. That's okay. That's excellent effort. See, this is natural. In very rare cases, we will have training error and testing error almost working together. Now, we can see here that as we move down, the training error keep reducing until it gets to 0. If somebody is too greedy, it's good to stop before you get to 0 and start running into trouble. Because as this training error is getting to 0, you can see the testing error that was reducing suddenly started going up. This is the challenge. That's why we have to make the bias variance trade-off. This is underfitting. If your model is operating at this level, we said it's an underfitted model because this is where it's cut stock. It cannot improve beyond this level. This is underfitting. Both the training error and the testing error, they are still very high. However, as you go down and you are able to take your training error to 0 or near 0, the testing error starts going up. You can see overfitting takes place now. Now, the trade-off you need to make is you need to be smart when you are building your model to be able to know where to stop. You see, you better stop at this point so that you get some error, but you are not going to run into this trouble of overfitting. Because as you keep going one way or the other, once your training error leads to 0, then memorization takes place. Then when the testing set comes, you are going to get very huge error. That is overfitting. So it means before overfitting takes place, you need to stop. This is the case for bias variance trade-off. Now, still on that, how can you try to solve some of these issues? You see, when you have many training errors examples, you are likely going to bring down some of your issue. But when the training example is very low, this is testing error. When you have training, one of the ways to solve underfitting or overfitting problem is to increase the number of your samples. If the samples are inherently, if the samples are very few, then you might easily run into overfitting problem, in which case, try to get more samples. There are experimental demonstrations that have shown that once the training examples increases, then you might be able to get testing error that is reasonably okay. However, with few training examples, then you might end up having very high testing error, which is characteristics of overfitting. However, it's good also to check different algorithms. Like we always say, there's no free lunch idea. So here, when you have error number of training example, you can see experiments also have shown that as you increase the number of training examples, See, the error of testing and training, we gradually try to converge together, which is what we're looking for, by the way. That is, we don't want a situation whereby the error from training will be so low and the error from testing will be high. Can we have a situation whereby a trade-off between them? So this is what you get when you increase the number of training example. Experiments have shown. So this is called the generalization error. The difference between the training error and the testing error is known as the generalization error. So the smaller, the better. This is what we want to achieve. We don't want the error of training and testing to be too far from each other. No, this is actually what we are trying to test. And that's what we call generalization error. So that when I run an experiment, I got the training set accuracy to be like 98% accuracy, and the testing set is also 97. That is excellent. You can see that the difference between the error is very, very minimal. And we've also had situation whereby the training performance was 99% and the testing performance was 100%. This is very rare. I've gotten this one time in all my experience as far as machine learning is concerned. Only one time. So the data set was really huge. It was Arabic number recognition. So huge number of data set were able to achieve this. It's very rare to have testing accuracy better than training accuracy. It can happen because generalization error is trying to make sure the difference between the two is very minimal. So it's very common to have 99% accuracy for training and 99 for testing, or 99 for training and then 98. That's okay. Sometimes you have 95 for training accuracy, and then also it's like 85. It's still okay. Because I've seen students, the moment they got 95 for training, and then they started getting like 87 for testing, they say, oh, this is overfitting. I don't know, this is not overfitting. It's not too far. But you can do your hyperparameter testing. You can try to check it more. Perhaps you can take it to a better level. But when you get overfitting, you're going to get really high accuracy, like 95 for the testing set, and the training set is going to be giving you like 23%, 45%. Then you have to start saying that, oh, I think my model is overfitted. See, because the gap between the training error and the testing error is going to be really very wide. Then you know that something is very wrong with the outcome of your model that you have developed. So this is what we mean by the overfitting and underfitting. We say, remember that no classifier is inherently better than any other. You need to make assumptions to generalize. So which algorithm is going to avoid overfitting? Some algorithms are known to quickly overfit. For example, neural network, the standard one, can overfit easily. Support vector machine has been reported with having a lot of internal mechanisms that can make it to prevent you from going into overfitting. Of course, depending on the kind of data set you are also modeling. So you have to choose different algorithm and then see which one works for your problem, because there's no algorithm that is better in all situations. So 3 kinds of error. We have inherent or unavoidable one, which I've explained, to come from the data set. We have the bias due to oversimplification, that, oh, this problem is very simple. Your model ended up not able to identify or to model correctly. And then due to inability to perfectly estimate a parameter from limited data, if your data is really very small or your data is not enough, you are likely going to run into problem of overfitting, depending on the kind of model you are using. That's why if your data is very few, techniques like support vector machine, hopefully one of these days we'll be able to look into support vector machine and what are the principles behind it that it's able to withstand few data set modeling, while other machine learning algorithms will fail. So because it has some unique capability, of course, as the case may be, there's no free lunch, no algorithm can solve all problems in perfect way in all situations. We always need to make assumptions, check different algorithms, and know when your model as overfitted and trying to see what can you do to stop the overfitting problem, as the case may be. So this is what we're going to have about underfitting and overfitting for today. We're going to give room for question and clarification, if any, from member of the class. Thank you very much for listening, and I wish you all the best. Thank you.